In this video, I wanted to go over a tool that I often use when I'm developing embedded software, and that is an oscilloscope, and particularly using it to time the duration of certain operations that otherwise would be very difficult to get an accurate read on how long they take. And so the basic idea is if there's some operation that I'm interested in timing, or figuring out how long it takes, very often I'll just take an unused digital I/O pin and then set its value high and then do the operation in my code and then set it low at the end of that, and then I'll set that up in something of a loop or something equivalent, or maybe something I can trigger once in a while, and then I'll look at that I/O pin on an oscilloscope and I'll look at the high time or the time between successive high times, however I've set it up, in order to accurately time how long that operation takes. And so I wanted to show you how to do that in an Arduino environment. And in the process I'll also talk about a faster way of manipulating the digital I/O pins than is afforded us by the conventional digital write function that comes in the Arduino library. And so you can see in the upper left-hand corner here in the picture, I've got the Arduino connected up to the same set of hardware that I've been using for some of the examples that I've been showing. This time I'm not really using any of these LEDs and push buttons and potentiometer at the moment, but I am using pin D13, which is what the green LED is connected up to, as the I/O pin that I'm going to monitor to time a certain operation. I'm ultimately interested in how long does it take to do an analog read operation, but before we get there, we want to know how long does it take to actually set a digital pin high, and how long does it take to set a digital pin low, so we can tell whether or not that's going to be a significant overhead in our time measurement. So at this stage we're interested in just timing the amount of time it takes to set a digital pin high and low using different mechanisms. So the firmware, or the sketch that I've got programmed into my Arduino, is this over here on the right. And I've got some pound define statements up here, and these are things that you may or may not have seen. I certainly have not made use of them in any of my example sketches. But what a pound define statement is actually something called a preprocessor directive. So before the compiler gets a hold of your code, it goes through something called a preprocessor, which does certain things. And one of the things that the preprocessor can do is include other source files in a particular source file. That's a pound include directive. And you can also have pound define. And what these can do for us is to define a name for something. And that basically is just substituted by the preprocessor for whatever is over here. So here I'm defining D0 underscore port to be port D. And so the preprocessor, wherever it sees D0 underscore port, it will substitute PORTD, all caps. And so this is like kind of a search and replace feature. So I've got a bunch of these things defined, one for each of the digital I/O pins. So D0 port is port D, and likewise up to D7 port is port D. And then I've got D8 port through D13 port, which are all port B. And so port D and port B are variables that are defined deep within the Arduino source files that basically define variables that map onto what are called special function registers inside of the microcontroller, which are things that we can use to control the I/O pins. And it so happens that D0 through D7 are controlled by the register called port D, and D8 through D13 are controlled by the register which is called port B. And so these are convenience if you like, aliases for port D and port B, which sort of signify a certain I/O pin that's associated with one of these ports. Likewise, I've got some defined constants here, which so D0 bit maps to OB0000001, which is just the number 1, but it's written in binary. So if you have a sequence of ones and zeros and you prefix it by 0b, it's interpreted by the compiler as a binary number. If you had an OX here, that would be signaling to the compiler that it should interpret the following digits as a hexadecimal number. And so sometimes you'll see people using hexadecimal or binary literal values in their C code. In this case, I'm using binary because it's convenient. I want to basically highlight that there's a single 1 in this group of 8 bits here. So D0 bit is basically the least significant bit being set high and all of the rest of the bits being low. So it turns out that in this port D register, the I/O pin D0 is controlled by the least significant bit. D1 is the next least significant bit, D2, D3, D4 kind of successively shift over here until you get to D7, which is controlled by the most significant bit in the port D register. And then we go back to the least significant bit when we get to the port B register, starting at D8 and going up to the bit 5, or the 6th bit, in D13. And so the idea is that if we want to set an I/O pin high, we can basically set to 1 the appropriate bit within the appropriate port register. And so we'll be making use of these convenience aliases here in order to set the I/O pins high and low by direct port manipulation, which turns out will be much faster than setting port pins high or low with, or digital pins high or low with the digital write function call. Another thing you can do with these pound define things is to define what are called macros, which actually are more complicated than the simple sort of aliases, because they can have parameters. And so we can define something that looks almost like a function call, but instead of being an actual function call, it basically takes instances of this thing here, in this case digital pin set of P comma B, and expands it into an expression, in this case, which is P or equals B. So whatever P appears in here, that gets put into this expression where the P is here, and whatever B is in the source code at this point gets inserted into where B is in this. So it's a very powerful sort of macro construct. And so we have this digital pin set, and then this will be a port, and then this will be a bit mask, actually. And what's going to happen is it's going to say that whatever this port register is equal to that port register ORed with bitwise whatever this bit mask is. And so if we take, let's say, port D and say that that gets assigned the value, whatever its current value is, ORed with this one, what we're going to basically do is not change any of the 7 bits, any of the 7 most significant bits, and regardless of what the least significant bit is, we're going to set its value high, because it gets anything ORed with a 1 is a 1. And so this will have the effect of basically setting a digital I/O pin high. We can do a similar thing with a bitwise AND if we flip all the senses of these bits. And so here I've defined a macro which is going to enable us to clear a particular bit in one of these registers. So bitwise ANDing the value of a port register with the complement of one of these bit masks is going to effectively leave alone every bit in the register that has a 0 in one of these positions, because those zeros will be flipped to a 1 by the complement operator, and anything ANDed with a 1 just goes through unchanged, if it was a 0. If you AND it with a 1, it stays a 0. If you have a 1 and you AND it with a 1, it stays a 1. But where I had a 1 here, that gets turned into a 0, and if you AND something with a 0, it's going to set it to 0. And so we can clear a particular bit, leaving all the other ones unaffected using this kind of bitwise AND operator. And I've got a digital pin toggle macro here, which is using a bitwise exclusive OR. And if we toggle something, if we exclusive OR a bit with a 1, it will toggle it. If we exclusive OR it with a 0, it will leave it unchanged. And so this is a way of just flipping the state of a given bit without affecting all of the other ones. And so we're going to make use of some of these and see how long it takes to toggle a pin or to set and clear a pin compared to the conventional digital write high and low that we're used to using at this point. So these are all pound defines. Eventually we'll put these into a header file so that we don't have to have them at the top of our sketch all the time. But here's the rest of the sketch. We've got our loop time function, our isItTime helper function that we've been using that handles the rollover of the millis timer. We've got a global variable which keeps track of the last cycle, if you like, loop time. And then we're defining a loop interval which is a constant 5 milliseconds. So our setup function is basically just going to set up pin D13 as a digital output, initialize its value low, and initialize the loop time variable with the current value of the millis timer. Then our loop function is checking the millis timer, and if it's time to do something because of the 5 milliseconds have elapsed, then what we're going to do is in the body of this if statement here. And what we're going to do is we're going to use digital write to set pin 13 high, then low, then high, then low. So that will toggle D13 twice using digital write. And then we're going to use our digital pin set macro to toggle or to set digital pin or D13 high. Then we're going to use the digital pin clear macro to set it low, digital pin set to set it high, digital pin clear to set it low. So we're going to toggle it twice using these macros. And then we're going to use the digital pin toggle macro that uses the bitwise exclusive OR just to see how long that takes relative to these. And then we're going to set the loop time equal to the millis timer, and the cycle will start again. So this should give us a repeated cycle once every 5 milliseconds, and then it's going to toggle the digital pin 13 in using different mechanisms several times. And so we're going to look at that pin 13 on an oscilloscope. And the oscilloscope that I've got set up here is an Analog Discovery 2, which has been behaving so far, but it just lost communications with my computer. Hopefully it will come back. And so we're going to run this, and we're going to see how long it takes. So you can see, that's not what I want it to do. I want the position to be 0, and I want the base to be 5. No, I want the base to be 1. That's what I get for making the mouse wheel go. So you can see that this is, actually I guess I had it at 2 instead of 1. So you can see there's some jitter here, but you can see there's a basic 5 millisecond sort of periodicity here. So every once in a while it looks like it's more like 4. So it's not perfect, but you can see that there's a very, very brief something or other going on here at the beginning of the cycle, and that's basically going to be the toggling of D13. And it doesn't take very long. It certainly takes much less than a millisecond. So we're going to have to zoom in to see exactly how long it takes, but let's go to 10 microseconds per division. So here we are zooming way in, and you can see that obviously the digital write function is taking quite a lot longer than the direct port manipulation, and so we can zoom in a bit more, and so you can see it takes to set the pin high and then to clear it. It's going to take something like in the neighborhood of 3.8 maybe 3.2 milliseconds, or microseconds rather. So the actual call to digital pin set may be back here somewhere. So it takes a while to get in there and set the value high, and then it returns, and then at some point the call to digital pin set or digital write low gets called, and it goes low, and then it takes, looks like about 3.2 microseconds here for the digital write function to do its thing, which is not a long time, but certainly much longer than we might like if we're timing something that's on the order of microseconds. So if our sort of setting the I/O pin high before the operation is a significant fraction of the total amount of time it takes to do the operation, and then setting it low represents another significant fraction of time, that could introduce some inaccuracies in our timing. So let's set this a little higher so we can see these things. So you can see that the digital pin set and digital pin clear macros are doing something on a lot shorter time scale than the digital write is doing. So it's like about 3.2 microseconds for the digital write function, whereas for I can zoom in here, 1 microsecond per division. It's certainly well under a microsecond for the digital pin set and digital pin clear combination, and it's a little bit longer, but still well under a microsecond for the digital pin toggle. So the reason for that probably is that the exclusive OR is a little more complicated operation and takes a little bit more time than just an AND or an OR operation. So if we maybe zoom in, say 500 nanoseconds here, and then we can shove this over a little bit. You can see that it takes about, let's see, this is half a microsecond. So it takes about, to do one set and clear operation, takes about 0.35 microseconds, which is a whole lot shorter than 3.2. To look at the digital pin toggle, it looks like this is about 0.4 microseconds rather than 0.2, so it's a little bit longer. I guess I said 0.25. Where did I go? So this is the pin write pulse, which is obviously a lot longer than these. So this was it's 0.4, 0.2, maybe 0.25. So these macros actually with the direct port manipulation are much faster than the digital write. So what we lose when we don't use the digital write is that we could pass an integer in here, whereas here we're passing effectively predefined constants, and we need to know which pin we want to manipulate. This isn't a variable that we can just stick here. So anyway, that's going to be a mechanism that we're going to use to time an analog read function. Okay, so let me stop this for the time being, and let's set this back to 0. And let's set this back to maybe, I want to know, millisecond per division. And so I have another sketch here, which is analog read speed. And as I mentioned, we can often we'll take a bunch of these kind of number defined or pound defined things and maybe some function forward declarations and some global variable declarations or something and put them in a header file. And so that's what I've done here with these port convenience definitions and these bit convenience definitions and my macro definitions. And so we can do pound include fast digital pin stuff.h, and if we have just single or double quotes here, it's going to look for this header file in the same directory as our sketches, and so this is living in the same project folder as the analog read speed source file. And it's just like this pound include basically just includes the source of that file directly in this file at this point. And so we've got our loop interval and our loop time and our helper function is it time, and we in this case have the pin mode for D13 set to an output and set D13 low, set the loop time and our setup function, and then in the body of the loop what we're going to do is again we're setting up a 5 millisecond loop time, and we're going to basically do 3 successive reads of analog input 0, which is the thing that's connected to my potentiometer here. And we're just going to do that and set pin 13, D13 high and low in between each one, so we can get a reading of how long it takes to do that. So we'll push this out to the board. And you can actually see a difference already. So here, there's a little bit of a glow in the green LED, which was not perceptible in the case of the digital write speed sketch, because that sort of few microseconds high time every few milliseconds is such a low duty cycle that the LED was not even perceptibly on. But in this case, the analog read takes long enough that we're actually able to see this LED turn on very dimly. So that gives us a hint that this is taking a lot longer than the digital port setting did. But let's just see how long. So we can run this and see. We zoom in. We make it 100 microseconds per division. We can see that it's taking a little bit longer than 100 microseconds to do an analog read. So we set D13 high. We do our analog read. That's the first one here, x equals analog read 0. Then we set D13 low with digital pin clear. And we do y equals analog read 0. Then we set D13 high again. And we say z equals analog read 0 and set it low. And so you can see these are pretty uniformly spaced. These edges are uniformly spaced, indicating that it does seem to take the same amount of time each time we call it. And that's maybe about 110 microseconds or so. Okay, so this is a way that we can use the oscilloscope to time operations. If we wanted to see how long it takes to do some sort of arithmetic operation, we could set a pin high, do our evaluation of some arithmetic expression, set it low. If we want to see how long does it take to do a serial print, we can do that using this mechanism. And so it provides us with a very nice tool to accurately time various operations that we care about. Okay, so that's it for this one. Thanks for watching.